Good morning, all. So today we will discuss comparative analysis among various machine learning algorithm. So we will take some algorithms which belong to unsupervised learning, and the rest are supervised learning, and then we will do the comparative analysis. Okay, so let me first start with algorithms like k-means, then we will go ahead with SVM, decision tree, random forest, and in later stage, we will also do an Python coding, that is the implementation of all these four algorithm to do a comparative analysis. Okay, so let me share first with k-means. So we will have a look on what is the algorithm called the k-means algorithm. Okay, so as you can see, the example of k-means which has been considered over here, that once you have a specific type of mixed communities and you would like to segregate every cluster, generally we make use of the KNN algorithm. So it's basically a classification type algorithm, and it works really well with unsupervised environment. Okay, like say, for example, you have two categories A and B, and there are certain data points, new data points being incorporated, and we need to place those data points either in category A or in category B. So if you see this example, the idea will be very clear that before KNN, we have considered category A, which is in the green color, and category B, which is on the golden color. And there is one data point available over here, which is in the dark blue color. And you can see when we are applying KNN over here, that specific new data point coming under the category of A. So that's actually the main idea behind KNN. So you can see the steps, what has been mentioned over here. So here our main intention is to calculate an Euclidean distance, which is very, very important over here, which actually determine the number of neighbors in any specific KNN algorithm. Okay, and this is how following a subsequent step, we can make our model ready. So first we will see that we have plotted a graph, and there are two specific categories, as I told you, and one new data point came into the picture. And we will start making an Euclidean distance. As you can see how we are selecting the Euclidean distance. So keeping a value of neighbor, which is very important in k-means, and this is the mathematical formula for getting the Euclidean distance between two specific point. As you can see, we have considered point A and point B, and we got the corresponding Euclidean distance. So this is one of the measuring parameter, and based on that, we can decide that a specific data point belong to category A or category B. So as you can see that for category A and for category B, we have considered, and ultimately the new data point will belong to a specific category based on the nearest neighbor. Which one is the nearest neighbor? Based on that, we can just put. So for A, nearest neighbor is 3, and for B, the nearest neighbor is 2. And based on that, we can actually put that in a specific cluster. Coming to the next algorithm, which is known as support vector machine algorithm. This is another popular algorithm, but this one is basically used for supervised learning strategy. That's one of the most important thing we need to understand. And generally, it's responsible for creating the best line or decision boundary, which can segregate two different or multiple clusters. And it can be in dimensional space also. We can do this particular type of segregation, isn't it? So let's select one example. So here generally what we consider is called an hyperplane. The middle line, as you can see in the diagram, is called an hyperplane. And on the right hand side, the dotted line is representing the positive hyperplane. On the left side, it's representing the negative hyperplane. And as you can see that there are various data points which are blue and green available over here. So generally, this is known as the support vector, and the hyperplane, this is also the maximum margin. And this is how we start drawing a line between two specific cluster. So generally, once you're talking about SVM, this is a little bit advanced compared to the previous algorithm KNN, what you have learned so far, and it's working on a supervised environment. And this is one of the example which is in front of you. You can see that whenever we have a specific data which is related to the animal like cat and dog, and we can select the corresponding hyperplane to give the proper classification. So based on this idea, we have two different type of SVM. One is known as the linear SVM. Once you have only two specific class to be separated, so we can do using a straight line. That's basically known as the linear SVM. At the same point of time, not necessary that there will be two class. There can be multiple classes also available. And then non-linearity, obviously one of the most important concern at that specific case. And we can separate those using a non-linear strategy, and that's basically called as the non-linear SVM classifier. So hence we learn two different SVM strategy, linear and non-linear. So the idea of hyperplane is very, very important. So there can be a single line or a multiple line, which creates the boundaries, which actually helps us to take the decision that how we can segregate two or more clusters from each other. Okay, and there are various features which is actually affecting the dimension of the hyperplane. As I already told you, there can be two features or there can be more than two feature. Okay, and once we have made the corresponding hyperplane, then we start applying the support vectors, which is nothing but the corresponding data points here termed as the vectors, as you can see. And we always start finding out that these data points, how they are closest to the newly created hyperplane. That's the main idea behind this particular algorithm, as we have understood over here. And let's have a look on a simple example to understand that how SVM is actually working. Like if we have a data set and which is having two specific tags, uh, like green as well as blue. So what we will do, we will take two specific features over here like x1 and x2 respectively. And we start making a classifier which is accountable for actually splitting the two different sets of green or blue. Like if you see this particular image, so this is scattered green and blue. And fortunately, this is very simple data points we have considered. Okay, and we can draw multiple lines, as you can see, which can split the green from the corresponding blue. And how basically we will start, we will make one boundary or region, which is known as hyperplane, as I already told you. And the goal of SVM always is to maximize this particular merging. So generally, when we are talking about making an hyperplane, we always use the idea called how we can make it optimal to maximize the margin. That's the core idea based on which SVM is actually working. As you can see this diagram over here, there are green points and as there are blue points too. And this is what my optimal hyperplane is. And based on that, I can find out the distance of the points, which is known as vectors. Here, the data points, basically, we are calling it a vector. And like that, we have drawn the dashed line, which is basically known as the margin, which has been fixed around the solid line, which is hyperplane. Correct. And this is what is the maximization of margin. That's called the optimal hyperplane in SVM. Coming to the next algorithm, which is basically known as decision tree. This is also another supervised learning algorithm like SVM, what we have learned, and it can be used for both classification as well as the regression strategy. So basically, whenever we start making any particular type of decision, it's very clear from the name, and we take help of the tree structures over here, what we have already studied earlier. And generally, the branch of that tree structure representing the test and the leaf nodes on that particular tree, which is also known as the terminal nodes, that actually hold the level of classification over here. Okay, so the tree is actually like a flow chart over here. As I told you, this is basically used for taking a decision. And here we will use an iterative process, a repeated process to split the tree as much as applicable. And we can stop whenever a specific criteria has been met. So that's the most important part, which is associated with the idea of the decision tree. So it can be the maximum depth of the tree, which can be taken into the consideration while we are making a decision tree. So let's have a look quickly with certain terminologies which we will use for the decision tree, which is almost same as the tree data structure you have learned so far, like the concept of root node, the topmost node, which actually represents the complete data set. Followed by that, the decision node or the internal nodes, very, very important, where you are giving an input feature. The leaf node generally represents over here a specific type of class or level, and splitting is one of the functions which has been used to split a specific node into two or more subnodes at any point of time. And the subsection, as usual, known as the branch or the subtree. So these are some basic terminology which is associated with the decision tree. Apart from that, we have the parent node, child node. Okay, so these are the certain concepts which is already known to you because you have already studied that in data structure. But the most important part over here is knowing about the impurity. The moment you start doing this particular work, applying a certain type of uncertainty or randomness, so we need to understand one very important terminology over here called Gini index or the corresponding entropy. These are actually the measurements of impurity. It means that whenever you start making a specific decision or a specific type of classification, how accurate your classification is, how accurate your decision is. That's basically measured with the help of this particular index, or it's also entropy is one of the concepts which we use, very important to improve the performance of the decision tree. Apart from that, variation, very, very important, which gives you a clear perception between the actual and the corresponding target variables, which may actually differ in different samples of the data set. Have a look on this particular diagram, which is giving you a right idea. Like suppose if I consider this subtree where you have a decision tree and you have different terminal nodes associated with the decision tree. So this is how the structure of the decision tree has been created. As you can see over here, like a tree structure where you have a root node, intermediate node, and the corresponding terminal or the leaf node. Have a look on this particular example, self-descriptive scenario. So as you can see, an animal tree we have made, and we would like to find out the animal who's having feathers, and based on that, we made the classification. In next step, again, we ask different type of questions to get a precise or accurate response associated with that particular classification. So this is how generally we create the decision tree. As I told you, we keep on splitting the nodes until and unless we reach to the criteria which we are looking for. So these are certain steps. Based on that, the decision tree works. Here I would like to mention one very important thing that is called ASM, or attribute selection measurement, playing a very important role, based on which you can select a specific attribute associated with a particular decision tree. And this particular process is repetitive or iterative in nature, as I have already mentioned. So these are certain steps which has been followed, starting with creating a root node, followed by using a strategy of making an attribute selection, and then we start dividing S into corresponding subset, and ultimately we keep on repeating the step until we are reaching to a specific level or beyond which we cannot have further classification. Okay, so this is what exactly is important. As you can see over here, the data has been split into train and test, and ultimately we start making a decision tree generation based on this iterative process where we are using ASM at the beginning and start breaking the data set into smaller subset until and unless we reach to a specific criteria. The same thing we also do with the test data to evaluate our corresponding model. And very important attributes, as we have learned earlier, accuracy, precision, recall is playing a very important role whenever we start evaluating a specific type of model. Precisely two very important components which is actually affecting the process of attribute selection. One is known as usual gain index, and another is known as the ID3 or information gain. So let's have a quick look. So if I consider a gain index, which is nothing but it's a probability of a specific variable being wrongly classified. Okay, if you can see this equation, it's very clear which PI is representing the probability of an object being classified into a specific class. And obviously here we are selecting in a random manner. So this is what is called the Gini index. And another one is ID3, which is also known as entropy. And it's actually help us to determine the feature or a specific attribute which is responsible for you to give the maximum information. Look at the equation which has been used for calculating the entropy, where the P is nothing the probability of E of S. And here the main concern is feature or attribute, which is responsible for generating the maximum information. Okay, and that's what is the most important requirement, as I told you, gain index and information gain while working with this particular algorithm. So there are a lot of advantages of decision tree, like in any business strategic decision, we can make use of this particular tree based on our available data set. And it needs very less preprocessing of data to incorporate the idea of decision tree. And we also make use of decision tree while solving any particular type of regression problem. As I told you, like while you are taking a decision for a specific product and start making a promotional strategy. So we can make use of this particular decision tree because it ultimately give you the prediction of profit or loss in a specific business. Applications like stock prediction, or maybe in any specific e-commerce transactions, whenever we start analyzing the data, we can make use of this decision tree algorithm. Lastly, we have an algorithm that's basically called the random forest, which is basically working on a supervised learning algorithm. And it's actually a kind of ensemble learning, because that's why we are using the term called forest, as you can see. And here we are also using the idea of the decision tree. Okay, and this can be used for both classification as well as for the regression process. So if we consider a classification process, then outcome we can say the class selected by most of the decision trees. So here the majority, a kind of voting process we are applying over here to get the classification task, as well as for regression task, we generally make use of mean or average prediction for the individual tree. So random forests can be applicable for both the strategy classification as well as the regression. So if you closely look at how this particular process is actually working, so I can say that here we are making multiple decision tree, and each decision tree is responsible for making a particular type of prediction. And that prediction is taken into the consideration that it can be either the values are averaged, which I told you just a few minutes back, used in regression, or it can be a voting system, which is used for the classification. Okay, so this is very important, and the features which you are using in the random forest makes it more strong for any particular scenario or circumstances to use. And this is the diagram. As you can see that there are two decision tree we have used, and ultimately we have taken the average of this two decision tree to figure out that how the results can be predicted. And there are various ways the random forest algorithm can be used. Like say, for example, you like to take a decision of purchasing a specific car, then obviously decision tree is very important, where you can check various types of features associated with a car, like it can be a number of seat, or whether there is a sunroof availability there in a particular car, and based on that we can make use of this particular algorithm. And as you can see, like buying a car, if we represent it with a workflow, number of seat, and based on that we have to decision buy or don't buy. And this is what exactly is the backbone of the algorithm, where the decision of the buyer is depending on various features like number of seat, sunroof. Apart from that, also we can make use of other features associated with that particular algorithm. Okay, so like that, we can make another decision tree for checking other facilities. Like as I told you, it can be quality of stereo or it can be comfort of seats. Any other features can also be used in this particular scenario. And ultimately, as you can see, now we are using quality of stereo or comfort level of the seat. And based on that also, you can have a particular decision whether to purchase or the car or not. And ultimately, once we start making a summation of all the decisions and start building a specific model and train the model also on the same way. So ultimately, we can reach to a specific decision. See here, we have incorporated various types of features all together, and thus it actually makes a specific type of decision tree. Okay, so this is really, really important whenever you're talking about any random forest algorithm, that how the features being extracted, what type of decision tree you are incorporating, what type of independent decisions being incorporated for those trees, isn't it? How we can combine those decision tree to keep an ultimate decision. That's what exactly is the main aim of this algorithm. Okay, so now coming to the comparative analysis, that's the next part which we would like to discuss over here. So in comparative analysis, basically what exactly we have seen altogether, that K-means is an unsupervised algorithm. So which is basically used for any kind of segmentation task. And obviously there are some pros and cons. Like pros is for a large data set, it is very simple. And first and the main task is to make the clusters. What exactly we have learned in K-means, we are just representing in a summary form. Apart from that, we do have the support vector meshes, which is used for text classification, image recognition, bioinformatics. And we have seen that how generally it works based on the idea of the hyperplane. And next to that, we have made use of the decision tree, which is a supervised learning algorithm, which is used for decision making. For example, credit card risk analysis, medical diagnosis. This is how generally we use, where we are taking a specific data and start splitting into a smaller sets. And this is very easy to interpret and visualize also, but it's more prone to overfitting at the same point of time. And lastly, we have gone through the random forest, which is a supervised learning strategy, again used for fraud detection, image classification. And this is completely depending on making the decision tree and start aggregating the results, where we can solve classification as well as the regression problem. Generally, it helps us to reduce the overfitting, and but it's a little bit slower at the same point of time. So if you see the comparative results, so this is what exactly we are representing over here, the comparative results of the decision tree, where we have taken all the algorithms, mentioned the category, the key strength, weakness, and a specific use case. And once you have gone through this particular table, you will get an idea about each and every algorithm which you have considered are working. And whenever a specific scenario has been given to you, you can decide which specific algorithm to be used. Like say, for example, whenever we are talking about do a credit list analysis for a loan disbursement. So obviously we will make use of decision tree. Or suppose we would like to find out fraud detection in e-commerce, then obviously random forest will be one of the best choice. Or we would like to go for an e-commerce customer segmentation, then K-means might be a good choice. So this is how the machine learning engineers are working also in the industry based on the scenario, based on the problem. So they can select a specific algorithm, or maybe more than one algorithm can be selected based on a specific problem statement. Let's have a look on Python implementation on the same aspect, that how practically we can make use of this algorithm to work together in a Python Jupyter notebook. As you can see over here, we have made use of different uh, model like the decision tree, random forest, k-means are all available inside scikit-learn. And we have also taken into the consideration about the accuracy score and the classification reports. So we have taken a very common data set which is available in Kaggle, that is called the IRIS data set, isn't it? And based on that, what exactly we have done? We have done a train and test split. As you can see, 70% data being utilized for training, 30% for the testing. So first we have started with k-means. So we have applied the fit function over here. We have taken the parameters like clusters and random state. Followed by that, we have taken an SVM, where you have taken a linear SVM with a random state. And again, we have incorporated fit method mostly in every algorithm over here. And followed by that, the predict method. Coming to the decision tree, we have done it in the same way. We have taken the decision tree classifier, and ultimately we have called the fit function over here, as you can see. And based on that, we are doing the prediction. Similarly, the same strategy has been applied for the random forest. Look at the evaluation part. So here our main concern is to get the accuracy score, which we did for all algorithms, as you can see over here. For SVM, decision tree, and random forest, as k-means is unsupervised, so we have not directly applied the evaluation matrix over here. And we have also incorporated the corresponding classification report for all the algorithm. Look at the output. So this is a kind of output which you have received for precision recall, as well as an F1 score for all the algorithm, classification report for SVM. And as you can see over here, all the scores being taken into the consideration. Followed by that, we have taken for the decision tree. Here also we have used the parameters precision recall F1 score, and similarly for the corresponding random forest, as you can see over here. So this is one small Python implementation, which is also giving you how comparative analysis we can do using Python. At the same point of time, we have also seen that how this algorithm is practically working. For that, we have imported time, and rest are all packages as usual we have taken from the decision tree, random forest, and k-means. And finally, here our main intention is to get the training time. Okay, so we have taken all these models. As you can see, all four models has been taken into the consideration, and we start measuring the time, which is the most important concern for this particular implementation. And we have taken the start time, the fitness function, and the corresponding end time. And finally, we have plotted that particular data. As you can see, with the different colors we have given for different algorithms, and our main purpose is to get the training time comparison and look at the outcome which we have received so far for k-means, SVM, decision tree, and random forest. Okay, so here we have plotted time, seconds, and we can see that how the value actually looked like, that what exactly is the time taken for doing a kind of training a specific model related to k-means, SVM, decision tree, and random forest. And as you can see that the values, and based on that, we can do a comparison that random forest, which is relatively high over here for the training time, whereas the decision tree is really less. And k-means, SVM, which is almost coming on the same range. So this is one of the clear perception from a specific data set that also we have to keep in mind. This is based on a specific data set, that is the IRIS data set, and we have used that particular data set on this code algorithm to get a training time comparison. So that concludes our today's session, that is a comparative analysis among all these four algorithms: k-means, SVM, decision tree, and random forest. Thank you for watching the session.